All right, let's talk about a tiny component that makes literally all modern electronics possible, the diode. You can think of it as a microscopic traffic cop for electricity, and it is absolutely fascinating. So here's our game plan. We're going to start with its basic building block, the PN junction. Then we'll see how to open and close this electrical gate, what happens when you push it way past its limits, and finally, how engineers actually put this all to work in the real world. Okay, let's dive right in. To really get what a diode is, you have to start at its very heart. It's this clever little piece of material engineering called the PN junction. The whole thing starts by taking two slightly different types of silicon and just sticking them together. One side, the P type, has a bunch of extra positive charge carriers. We call them holes. The other side, the N type, has a surplus of negative electrons. And that line right where they meet, that's the PN junction. Now, as soon as you put them together, something really cool happens. The free electrons from the N side immediately jump over to fill the holes on the P side, but only right there at the junction. This creates this neutral zone, which we call the depletion region. Think of it like a wall or a barrier that stops any more charge from crossing over. So, we have this barrier. How do we get electricity to actually flow through it? Well, we've got to give those charges a little push in the right direction. And we do this by applying a voltage in what we call the forward direction. By hooking up the positive end of a battery to the P side and the negative end to the N side, we start forcing the charges toward the middle. The positive voltage repels the holes, and the negative voltage repels the electrons, squeezing them both towards that central barrier. And the result? That depletion region gets much, much thinner. Okay, so with that barrier lowered, carriers can now just flood across the junction. This graph actually shows that excess concentration, it's a huge number of carriers being injected into the other side. That massive movement of charge is what we measure as electrical current. The gate is now wide open. So look, the most important part of this equation isn't all the letters, but the relationship they describe. That little e there stands for exponential. What that means is once you get past that initial barrier, even a tiny increase in voltage causes a massive exponential jump in current. It's not a gentle trickle, it's like a floodgate bursting open. But what happens if we flip the battery around? What if we try to push the current the wrong way? Well, that's called reverse bias, and it's how the diode acts like a closed gate. And here, you can see the exact opposite effect. With the battery flipped, the positive terminal is yanking on the electrons, and the negative is yanking on the holes. So instead of pushing them together, the voltage pulls them apart, away from the junction. And that insulating depletion region, it just gets wider and stronger. With this huge barrier now in place, almost no current can get through. I mean, there's a tiny, tiny leakage current, but it's so small that for all practical purposes, you can just call it zero. The gate is slammed shut. The diode is doing its main job, blocking current from flowing backwards. But, what if we don't take no for an answer? What happens if we just keep cranking up that reverse voltage, pushing the diode way, way past what it was designed for? Eventually, something has to give. Depending on how the diode is built, one of two pretty dramatic things can happen. In some diodes, the electric field just becomes so intense it literally tears electrons right out of their atoms. That's called the Zener effect. In others, the few carriers that are moving get accelerated to such insane speeds that they start crashing into other atoms, which creates this massive chain reaction, an avalanche of new carriers. Both of those sound pretty violent, right? Like an atomic-level car crash. So, is that it for our little component? Is it toast? Surprisingly, no. As long as you have something like a resistor in the circuit to limit the current so the diode doesn't overheat and melt, this breakdown process is perfectly fine and repeatable. In fact, some diodes, which we call Zener diodes, are specifically designed to operate right in this breakdown region. It's a feature, not a bug. Okay, so we've gone through all the deep physics. But how do engineers take all this knowledge and actually use it to design things? Let's take a look at how you analyze a real circuit with a diode in it. This is about as basic a circuit as you can get. You've got a power supply, a resistor to keep the current in check, and our diode. The fundamental question we always have to ask is, what is the exact current flowing through here? And what is the exact voltage right across that diode? A really elegant way to solve this is to just look at it visually. See, on one hand, the diode has its own rules for how it behaves. That's this unique exponential curve.
But on the other hand, the resistor and the power supply also have their own relationship, and that creates a simple straight line we call the load line. So, here's the magic. The circuit can only operate where these two lines cross. That single intersection point, which we label Q, is the operating point. It is the one and only combination of voltage and current that makes both the diode and the rest of the circuit happy at the exact same time.
This right here shows a classic engineering trade-off. That curvy exponential graph on the left is the reality, but doing the math for it is, well, it's messy. So for a lot of everyday work, engineers just approximate it with a much simpler model, like the one on the right. We basically just pretend it's a perfect switch. It's not 100% accurate, but it's often good enough to get the job done fast.
And that brings us to a final, really important thought. If we can just treat it like a simple switch most of the time, why did we bother with all that stuff about depletion regions and exponential curves? Well, because understanding the deep physics is what tells us when our simple models are good enough, and more importantly, when they're going to fail. That foundation is what all the clever engineering is built on top of.